Last time, we introduced summation notation, what is a sum, and calculated a few sums. And the whole reason we did that is to get ready for this section, Riemann Sums, which is fundamental to calculus. It's quite important. But before we get into those, let's do a few examples to motivate the idea, and the examples come from running. So here, let's suppose I run, I'm just going straight, like this, and I run at a constant velocity. I'll add that word. Constant velocity of 12 feet per second for 10 seconds. How far do I travel? Well, you might have already answered the question before I wrote anything down. We travel 12 feet per second for 10 seconds. The answer is 120 feet. And if you want to check units, for example, this is feet per second, this is seconds, and then we get feet when we multiply. Now, what's important to understand, or the way I like to think about this and begin with this, is let's look at a graph of velocity. So I'm running for 10 seconds, and I have constant velocity 12, okay? So my velocity function is here. It is a line segment. And this number 120, well, it's this area here, right? Because what is this area? Well, it's 12 times 10. So this area is 120. Okay, well, now let's change the example just slightly. Suppose I change my velocity as I run, and let me just draw a picture or graph of my velocity function. I will still run for 10 seconds. Okay, so for the first 4 seconds, I will go 12 feet per second. That's here. And then the next 4 seconds, I will go 10 feet per second. And the last 2 seconds, maybe I'm very tired and I just run 6 feet per second, like this. Okay, so now this is my velocity function, v of t. And I should have labeled the one over here, v of t. This is time t, this is time t. Okay, very nice. Well, the question is still, how far do I go, or what is my displacement? And still, it's an area. What we would do is we would just take, for the first 4 seconds, I go 12 feet per second times 4 seconds, and then I go 10 feet per second times 4 seconds, and finally, I go 6 feet per second times 2 seconds. So the units in each one of these are in feet, and we can just add up. This is 48 plus 40 plus 12. I've traveled altogether 100 feet. And as I mentioned, this is area of rectangles also, because what is this? This first term is this area, and then this second term in the sum is this area, and the third term in the sum is this area, okay? We can think about this sum a little bit differently. This, and this are the change in time, right? This 4 is really 8 minus 4. This 2 is 10 minus 8. It's the change in time, and this is the height, okay? So we can consider this the area here, or the total displacement, as, I'll just write it this way, it's a sum of the height of the rectangle times the change in t. right? And I didn't put indices. I don't really have indices here, but this is an idea of how we can think about this sum. And we will see this even more so moving into Riemann sums. Okay, now let's do one more example before I define Riemann sums. I will still do running, but I'm going to change my velocity even more. Now I will start slowly when I run and then speed up. And my velocity has the function 1 over 12 t squared for t between 0 and 12. And so a graph looks something like this. Well, I can approximate the total distance traveled, or I will call this also, it's really displacement but as I'm only moving forward and not backward, these two would be the same thing in this case. So I can approximate this with rectangles. I'll say areas of rectangles, which will be very similar to what we did in the last two examples, except those weren't approximations. Here we will do approximations. So what are the rectangles I'm talking about here? Well, what I can do is make this rectangle, make this rectangle, make this rectangle, and make this rectangle. Now, the height of the rectangles are the function values. So v of 3 is the height of the first rectangle, v of 6 is the height of the second, v of 9 is the height of the third, and v of 12 is the height of the fourth rectangle. So let's calculate these four values now. V of 3 is 1/12 times 9, which is 3/4. V of 6 is 36 over 12, which is 3. V of 9 is 81 over 12, which is 27 over 4. And finally, V of 12 is 12. And so to approximate this, the approximation here, so the approximate total distance or displacement I've traveled is, well, we take first the area of this rectangle, which is 3/4 times 3, and then we take the area of this rectangle, which is 3 times this here, which is 6 minus 3. Okay, plus the area of this rectangle, which again is length times width. V of 9 is 27 over 4, and then we have 9 minus 6. And finally, the area of this rectangle, which is 12 times 12 minus 9. And all of these, the width of the interval is constant here. These numbers are all 3. And this gives not my exact distance traveled. It gives an approximation. Okay, now what is this number? This is 67.5 and would be feet, okay? And what we have done, without even defining it yet, but I'm about to, this is a Riemann sum. And so now let's get into the precise definition. First, let's define a partition, P, of an closed interval a to b into n subintervals. This is an ordering where a is x0 less than x1 less than x2 less than all the way out to xn, which is b, and xi minus 1 to xi, this is the ith subinterval. When we do this, maybe I will change colors for this. Delta xi, okay, and this is the delta from the difference that we briefly touched on in the last video. Delta xi is xi minus 1. This is the length of this subinterval. The mesh, this is denoted like this. This is the maximum length of a subinterval in your partition. Now, just to connect this with this running example with function 1/12 t squared, I will just mention in the last example, what did we have? Well, our partition P, first of all, we were running from 0 to 12. That's our closed interval. And the partition, it always includes the endpoints. Okay, you see that here. And then we had 4 subintervals. We had 3, 6, and 9 were also in our partition. And you see here's 1 subinterval, 2, 3, and 4, like this. And then we had delta, well, it wasn't delta x, it was delta t, but we had delta t I was 3 for each subinterval. One more thing to add, and that is a set S of sample points for the partition is just a collection, say SI, where SI is in xi minus 1 xi. So for each subinterval, and there are n of them, you have a point in each subinterval. This is a collection of sample points. Now, with these definitions, we are ready to define the Riemann sum. So what do we need given a function f of x on a closed interval? So this is one thing we need. Oh, I'll put a bullet here. Then we need a partition P of this subinterval, and what that means is that we have, from this partition, we have a is x0 less than x1 less than xn, which is b, and we have this delta xi, which is xi minus 1. Both of these come from having a partition. So we need a function f, we need a partition p, and then given s sample points of this partition, and this means that we have a little si in this subinterval. Okay, so we need all 3 of these things for a Riemann sum. 1, 2, 3. Then The Riemann sum well, it's a sum, and I goes from 1 to n, so we're adding over these sub-intervals. We have f of si times delta xi. So we multiply the function value at this sample point times the length of the interval. And this, well, we'll look at some pictures in a minute, but this is precisely what we did in the last example. We had the areas of these rectangles, and this is exactly what this sum is calculating. Now the notation in our text is as follows. It's R, P, S of F. And this is, may or may not be in other texts, but we read our text and we work problems from our text. This is the textbook's notation. And one nice thing about the notation is in the notation we see sort of all three things we need for the Riemann sum. We need a function, we need a partition, and we need some sample points. Now, there are some special named Riemann sums, and what are these? So the special named ones have to do with what are the sample points. So I'll just mention these now. If Si is xi, this is called, well, let's look over here. This is the subinterval, and I'm saying that Si is the right endpoint. What do you think the name is? It's called a right Riemann sum. And this is what we saw in our example. I used the right endpoint to construct the heights of the rectangles. Another one, you can take Si to be xi minus 1. Well, again, look at the subinterval. It says Si is the left endpoint, and this is called a left Riemann sum. And finally, another one that is fairly common to see is that Si is, well, you would take halfway in between, and this is xi plus xi minus 1 over 2. This is called midpoint Riemann sum. And these three are the most common that we see and that we will practice: the right, left, and midpoint Riemann sum. And it's really telling you which points to evaluate your function at, which points to make the heights of the rectangles. So now, before we do anything else, let's do some examples. Well, let's begin with not too terribly hard of an example. We have the function x plus 1 on the closed interval 0 to 4, and I'm handing you the partition. It's 0, 1, 2, 3, and 4. Maybe I can write these points below. Here's 0, 1, 2, 3, and 4, and then 0, 1, 2, 3, and 4. And I have at least the function graph twice. We will do left, right, and midpoint. So maybe I will just start with left and right, and then I'll erase and redraw the graph for the midpoint Riemann sum. Okay, now the first thing to observe immediately in all three of these, you see delta xi, maybe I'll write that here. This length of this subinterval, the length here, the length here, the length here, it is 1 for all I. So we have a constant delta x, which is something that comes up a lot in practicality, but in this case, delta xi is 1. Okay, well, we will start over here with the left Riemann sum in this picture. And what that means is that this sample point is the left endpoint. So this will be xi minus 1. Now let's draw the rectangles and then we will calculate the Riemann sum. So we take the left endpoint, it's here. This is our first rectangle. We take the left endpoint, it's here. This is our second rectangle. We take the left, okay, it's here, our third rectangle, and finally we get this one. And the Riemann sum, which we'll write below, gives us this total area of the rectangles. Okay. What we want is a sum I equals 1 to 4 f of xi minus 1 times delta xi. But this is just 1, so let's start writing out the terms and we will see, well, this will be f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1 and then plus f of 3 times 1. And this is this area. This one is this area, and then the third rectangle area, and finally the fourth rectangle's area. Okay, the function value is x plus 1, so we get 1 plus 2 plus 3 plus 4, and this is 6 and 4, this is 10. Now you notice here, if you're thinking about the area, if we looked at the area underneath this curve or this line segment, this is really an underestimate here of the area, because you see there's white space. Okay, so it's an approximation of this area underneath the line segment, but it is an underestimate. Okay, maybe I should write that, of total area. And this was our answer. Okay, now let's move into the right Riemann sum. And the right Riemann sum, this SI is the right endpoint of the subinterval, XI. And let's draw the rectangles in this case. Well, here would be the right endpoint, like this, right? And then similarly here, this rectangle, we get this rectangle and this rectangle. And so the Riemann sum gives us the areas of these four purple rectangles. And we will see, similarly, this one will be an overestimate because we have this extra part of area in these four rectangles that exists underneath the curve. But the Riemann sum here is a sum I equals 1 to 4 f of si times delta xi. And again, delta xi is constant. It is 1. It's the same partition. So this is f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1 plus f of 4 times 1. And this is, again, the function value is just x plus 1. So this is 2 plus 3 plus 4 plus 5. This is 14. And as I mentioned, we can see graphically this one is an overestimate of the total area. Okay. Now, what's left to do, and I will have to erase because as you see, I have no space on my board. What's left to do is the midpoint Riemann sum. This is what we found for the left Riemann sum. The value was 10. The right Riemann sum, the value is 14. And the midpoint Riemann sum is what is remaining here. SI is halfway in between, like this. And let's just draw the corresponding rectangles on this graph. Well, we take halfway in between. This is 1/2. Okay, this gives the height of this rectangle covering the entire interval. Halfway in between is 3/2. And this gives us the height of the rectangle covering the entire interval. Here we have 5/2 is halfway in between. Here is the rectangle. And finally, 7/2 is halfway in between. And here is the rectangle. So our Riemann sum is giving us the area of these 4 rectangles. Okay, so let's write that now. Well, just like the first two, this is the sum, I is 1 to 4. It'll be f of this, which is xi minus 1 plus xi over 2, and then times delta xi. Again, delta xi, well, I had it above, but it's now erased, but it's 1. Okay, it's just this length. It's 1 for each subinterval. And so this will be f of 1/2 times 1 plus f of 3/2 times 1 plus f of 5/2 times 1 plus f of 7/2 times 1. Okay, the 1 is very at the corner, but it's there. Now, what is this? Well, the function value is just here, x plus 1. So this is 3/2 plus 5/2 plus 7/2 plus 9/2. We get 16 and 8/2, which is 24/2 or 12. Okay, and you see that in this example, this midpoint Riemann sum sits between the left and the right, and it certainly makes sense that it would if you think about the graph of the function. This example is kind of in the spirit of the first few we do, in that we have velocity and we're interested in displacement. But instead of giving an explicit formula for the function, what we have is we have a car traveling for 1 hour and we have the velocity measured at 4 times. Okay, so at some time between 0 and 12 minutes, the velocity is measured 40 miles per hour. At some time between 12 and 30 minutes, the velocity is measured at -10 miles per hour. And this means that the car is going backwards with the negative. At some point between 30 and 40 minutes, the car is traveling 20 miles per hour. And then finally, the last measurement at some time between 40 and 60 minutes, well, you see the car is stopped 0 miles per hour. And we want to use a Riemann sum to approximate total displacement. And just to add as a comment here, this will not be the same as distance traveled because we do see a negative velocity. But before, well, I don't have a lot of space to work the problem, so before I do, let me put in a little box some things over here. First of all, our answer for total displacement will be in miles, and this is in miles per hour. We want our interval to be hours, and it's 1 hour. So even though this is in minutes, we want to use the interval 0 to 1, okay? And then we can read off, so we have 4 subintervals here, and we can read off the partition just by looking at the endpoints of the subintervals. So my partition P is, I'll put it here, well, we have 0, and then we have 12, 30, 40, and 60, but all divided by 60. So 12 over 60, 30 over 60, 40 over 60, and maybe I'll just write 1 so that I can fit it here. So I will just leave these as number over 60 instead of writing them in lowest terms. But this is the partition. Maybe I will change this to an equal sign. Okay, so let's graph this before we write down the Riemann sum, and I will show you the rectangles. Well, the maximum height that we see is 40, but then I need to go down to minus 10, and then this would be 10, 20, 30, 40, and then we have 20. Okay, so here's some different heights. And then my partition, 30 over 60 is here, it's a half. Then I have 40 over 60. And then I have, maybe here would be 12 over 60. So you notice here my delta ti, if you think about these being times, it's not constant like the last example. The lengths of these intervals are not all the same. Okay, so maybe I'll plot the rectangles in green. The first subinterval here, 40 miles per hour from 0 to 12 minutes, okay? This is the height that we use for the rectangle. And then the second one is negative 10, so it's down here. And the third subinterval is 20 is the height. And the last subinterval, the height is 0. Now, the Riemann sum is not the total area of these rectangles because, for example, here, this is negative. So this rectangle, technically the rectangle has positive area, but this piece in the Riemann sum comes with a minus sign because of the function value. So it's more thought of as something called signed area, which we will certainly discuss more about that very soon. But let's write down the Riemann sum now. Okay, well, we have 40 miles per hour times this length of the interval, which is 12 over 60, and then plus minus 10 miles per hour times, well, the length of this interval is 30 minus 12 over 60, and then we have plus, we have 20 times the length of this interval, which is 40 minus 30 over 60, and it looks like I have no more space except the last interval, the height is 0, so we have plus 0, okay? Now we just add these numbers. Let's see, we get 480, we have minus 180 plus 200 all over 60, which is 500 over 60, or it's approximately 8.33. So this is our answer here. And this is an approximation, right? We don't know the actual velocity function. All we have is the velocity at these 4 times, and then we use these rectangles and the Riemann sum to approximate the total displacement. This is in miles, okay? This example, it's a little more standard perhaps than the last one where we are given a function. We're given a closed interval, and then we're told what type of Riemann sum and that we want 3 subintervals of equal length. So before I begin, maybe I'll just make a comment in a box. If we have the interval A to B, and we want n subintervals of equal length, because this does come up quite often, and so let's take the time to discuss it before we work this problem. Well, this delta xi, which comes up in the Riemann sum, because they're equal length, I will often just write delta x, because it's all the same. The subintervals have equal length. And what is this length? This would be b minus a, the length of the interval, divided by the number of subintervals. So b minus a over n. Okay, so we can use that here. In fact, we need that here. This is part of starting the problem. Okay, well, we have the interval, 3 subintervals of equal length. Delta x is 7 minus 1 over 3, which is 6 over 3 or 2. And once we have delta x, we can write down our partition, the partition P. Okay, well, it always has here the first endpoint, or the endpoint of our interval, we should say, and then you march forward by delta x until you arrive at the other endpoint of your interval. So this would be 1, 3, 5, and 7. And you can count to make sure you have 1, 2, 3 subintervals. Okay, looks good. Now, here is a graph of 1 over x on 1 to 7. And let's draw the rectangle. So we want midpoint, right? The midpoint between 1 and 3 is here at 2. The function value is 1/2. And so here is the rectangle. And then here, the midpoint between 3 and 5 is 4. Here is the height. It's at 1/4. And then finally, for the third subinterval, the midpoint between 5 and 7 is at 6. And we have this subinterval. Okay. Now, the Riemann sum will give me this area plus this area plus this area. Okay, so let's do that now. I'll write it, the sum I equals 1 to 3. F of Si delta x. This is the Riemann sum. This is, well, maybe I'll do it in 2 steps. It's f of 2 times 2 plus f of 4 times 2 plus f of 6 times 2. Right, this is the delta x. We've already calculated it. And the function is 1 over x. So this is 2 over 2, or 1. This is 2 over 4, or 1/2. This is 2 over 6, or 1/3. And here, maybe I should have left 6 in my denominator because I have 6 plus 3 plus 2. This is 11 over 6. So this would be the value of this Riemann sum. Let's compute the left Riemann sum for f of x is sine of x on 0 to pi using 4 subintervals of equal length. Then I have graphed sine of x. We don't need sine on its natural period of 2 pi, just between 0 and pi. And then if we begin calculating delta x, this would be pi minus 0 over 4, which is pi over 4. And immediately we can write down our partition, P. We always start with the left endpoint, and then we march forward by delta x until we arrive at the right endpoint. So this would be pi over 4, this would be pi over 2, 3 pi over 4, and finally pi. Okay, so let's draw. I need to add these points of the partition here, pi over 4, and here 3 pi over 4. It's a left Riemann sum, so I use the height of the left endpoint here. So this first height 0, and then here I use the height from the left endpoint. Here I use the height from the left endpoint. And here I use the height from the left endpoint. Okay, so this area of these 3 rectangles, really 4, but this rectangle has 0 area, but this area gives us the Riemann sum. So let's write that down now. Okay, what we want is a sum I equals 1 to 4 of f of left would be xi minus 1, and then delta x, where delta x is pi over 4. This is equal to Well, we see by looking it's 0, but maybe I will just include it. It's sine 0 times pi over 4. That would be I equals 1. And then we have sine of pi over 4 times pi over 4 plus sine of pi over 2 times pi over 4. This is 1, 2, 3. The last one is the sine of 3 pi over 4 times pi over 4. Okay, this is the Riemann sum. And as I mentioned, this first term is 0. Sine of pi over 4 is square root 2 over 2. And then sine of pi over 2 is 1. And again, sine of 3 pi over 4, well, it's another square root 2 over 2. Okay, so all together we have, oh, I can write it this way, pi over 4 times, I have 1 plus the square root of 2. And this would be the value of this Riemann sum here. Here's my last example, and perhaps I won't graph this one just to illustrate that you don't have to draw the rectangles every time just to calculate a Riemann sum. And then when we're finished working the problem, I will show the picture of x squared on this closed interval with 5 intervals and a right Riemann sum. Okay, so the first thing we want to do is calculate delta x. This is b minus a over n, like this. The numerator here is 5 halves. 5 halves divided by 5 is 1/2. We may immediately write down our partition. And just like the last two examples, we start with the left endpoint and we march forward by delta x until we arrive at the right endpoint. Okay, and then you can make sure, and it's a good idea to check, we have 1, 2, 3, 4, 5 subintervals. And as I was mentioning, this is a right Riemann sum, which means we will be using the right, this one, this one, this one, this one, and this one, the right endpoints of each subinterval for our height. Okay, so we want to sum I equals 1 to 5 as f of xi. That's the right endpoint, and then delta x. Okay, the function value is x squared, so we get minus 1 squared times delta x plus minus 1/2 squared times delta x plus 0 squared times delta x plus 1/2 squared times delta x. And this, if you count, this was I equals 1, I equals 2, I equals 3, I equals 4. We have one more, and that's using 1, so 1 squared times delta x. Okay, this is our Riemann sum. Now let's figure out what this is. This is 1/2 plus 1/8 plus 0 plus 1/8 plus 1/2. Okay, we have 4 plus 1 plus 1 plus 4 all over 8. This is 10/8 or 5 over 4. So this is the value of this Riemann sum. And you see, I could calculate it without drawing a picture, although the picture can be helpful. So now let's look at a picture of this graph, x squared on the interval minus 3/2 to 1, and we will be able to see this right Riemann sum.